Hello and welcome back. It's time to solve another truss. Let's solve this one here. So let's begin by looking at the truss, creating a free body diagram and deciding if this truss is determinate. Let's go for it. So first things first, creating a free body diagram, and I'm going to replace this roller with a reaction force. We'll call that H4, and here in place of this pin support, I am going to create these two forces representing the reactions V1 and H1. Next thing we're going to do, we are going to determine if this truss is determinate. We do that by figuring out how many unknowns we have. Unknowns are the number of reaction forces and the number of members. In terms of reaction forces, we have 3. In terms of the members, we have 5. That gives us a total of 8. Our knowns are the number of equations we can solve. For a truss, it is 2 equations per joint, so 2 times the number of joints. In our case, 2 times 4, and that is 8. Since the number of unknowns equals the number of knowns, this truss is determinate, and we can solve it using the method of joints. Step 2 is going to be finding the reactions. If I look at the reactions on my drawing, I can see that there is only one reaction in the vertical direction, V1. So after I decide on the directions for my positive sign convention following the right-hand rule, which is this, right-hand rule, I can do some forces in Y to determine that reaction, because it's the only thing that's unknown in the vertical direction. So I've got V1, and then I've got minus 20 at joint 2, I've got minus 30 at joint 3, and don't have anything else in that vertical direction, so that equals 0. And from here I can find out that V1 equals 50 kilonewtons. I'm just going to highlight that. The second thing that I can do, I can go and do moments around joint 1. And I chose to do it around joint 1 just because that way I eliminate both V1 and H1 because they pass through joint 1. The 30 kilonewtons at joint 3 also passes through joint 1, right, because its line of action passes through. And also that force of 25 at joint 2, its line of action also passes through joint 1. So I do not have to consider them. So I'm left with the external loads of 40 and 20 and H4. So let's do that. Let's start with H4. H4 creates a positive moment, so plus H4, and the distance is 4. And then I have the 40 at joint 3. That creates a negative moment, so minus 40, and the distance is 4 as well. And then I have the 20 at joint 2, also a negative moment, so minus 20 times 4 equals 0. So let's have a look what we have here. We have 4H4 minus 160 and minus 80 equals 0. So 4H4 equals 240, and H4 therefore equals 60 kilonewtons. Okay, let's just highlight that. And then the last thing I can do is I can do the sum of forces in the x direction equals 0, with that being the positive direction. So I've got H1 minus H4, those are my two reactions, and then I've got plus 25 and plus 40 equals 0. So H1, which is my only unknown at this point, equals H4 minus 65. So I end up with minus 5 kilonewtons. Let's put these back on our drawing. So H4 worked out as 60. So let's replace this with 60. V1 was 50. So let's replace V1 with 50. And H1 came out as negative, which means that we assumed that it was going to the right. It's in fact going in the other direction. So let's put it in its correct direction and correct value. So we have 5 kilonewtons going this way. And that's the reactions. I can do a quick check just to make sure that I got all those reactions correctly. And I can do the check by doing the sum of moments around, say, joint 4. So around joint 4, I've got, from joint 2, I've got 25 in the positive direction, so plus 25 times 4. The 20 at joint 2 passes through, so that doesn't contribute to moment. If I go to joint 1, I've got minus 50 times 4. And I've also got minus 5 times 4. At joint 3, the 40 passes through, or the line of action of the 40 passes through, and I've only got the 30, which contributes a positive moment, so plus 30 times 4. And if we sum all of that, we will find that that indeed equals 0. So brilliant. That's a quick check on my reaction forces. So once I have my reactions, I can proceed to solving using the method of joints. If I look at my structure, I can see that joint 1 and joint 3 have 3 unknown members at them, so I cannot start there. But the other 2 joints have only 2 unknown members at that joint, so I can start at either one of these. Let's begin. So let's start off with joint 2. Let's draw everything out. I'm using purple to draw the internal forces that I do not know. So I have F2, 4, and I have F1, 2 here. I also have these external forces of 25 and 20. And since everything here is at 90 degrees, this is a pretty quick and easy solution. So let's do sum of forces at x equals 0, with this being the positive direction. I have 25 minus F12 equals 0, so F12 equals 25 kilonewtons. Looking now at the sum of forces in y equals 0, with this being the positive direction, I've got F24 minus 20 equals 0, so F24 works out as 20 kilonewtons. And that's it, we've already got 2 members. Let's just write them in our graphic. So 1, 2 we said was 25 and 2, 4 was 20. And just a reminder, because I assumed that everything was in tension and everything came out positive, these members are indeed in tension. Let's move on to joint 3, which will be a simple joint as well. So once again, I'm going to draw the forces in the members in tension. So I have F3, 4, and I have F1, 3. I also have these external loads of 30 and 40. And let's start off with the sum of forces in the y direction this time, with this being the positive direction. So here I've got minus 1.3 and minus 30 equals 0. So F13 equals minus 30 kilonewtons. In a similar way, we can go for the sum of forces in the x direction equals 0, with this being the positive direction. And here I have F34 plus 40 equals 0. So F34 equals minus 40 kilonewtons. And let's go and draw them back on our truss. So 1,3 was minus 30 and 3,4 was minus 40. And as we know here, because these two came out in minus, and I'd assumed initially that they were in tension, it means that both of these members are in compression. And now we only have one more member to find. So looking at the truss now, I can see that I can go to either joint 1 or joint 4, it doesn't matter, both of them only have one unknown. Let's go to joint 1. Once again, I'm going to draw all the internal forces in tension. So I've got F12, I've got F13, both of these are found, and I've got F14 here. I've also got these two reaction forces, 50 going this way and 5 going this way. And I do know that the angle here, alpha is 45 degrees, right? Because this is 4 on 4. It doesn't really matter where we start. Let's start off with, say, sum of forces in x equals 0, with this being the positive direction. So I've got F12 in positive x, I've got minus 5, right, because the 5 is in the negative x direction, and I have a component of F14, so I've got F14 cos 45, or cos alpha. That's all I have in the x direction, so that equals 0. So F14 is going to be 5 minus F12 divided by cos 45, and that is 5 minus F12 is 25 divided by cos 45. So here I've got minus 20 divided by cos 45, and that equals minus 20 square root of 2 kilonewtons. Now let's check that. So right now we have found everything that we need to find. We have all the members. Let's just write this last one here, minus 20 square root of 2. But let's do a few checks, okay? So let's start off by using the y direction as our first check. So in the y direction, we've got 50. We've also got F13, and we've also got a component of F14 sine 45. So that is 50. F13 we already found, that is minus 30, and here we have F14, which is minus 20 square root of 2 sine 45. If we work that out, that works out as 50 minus 30 minus 20. Does that equal 0? Yes, it does. So our first check gives us a good indication that we have solved this truss correctly. We can now go on to joint 4 and do checks in the x and y direction there as well to just double and triple check that we're correct, but I'll leave that up to you. That's it for this tutorial. Join me again for another one. Bye for now.